Good evening, everybody. Welcome to day one on week 4 of the semester. The last topic that I mentioned in the videos was the whole idea of naming ionic compounds. Understand that when it comes to exam 1, the material from chapter 3 is going to conclude where you guys are going to be able to produce the name of an ionic compound given a chemical formula, like the problem that we see here, or if you're given the components or you're given the name of those ionic compound, then understand that you need to come up with the chemical formula. So make sure that you practice. I will have office hours this week, so make sure that you check that out. I also put on Canvas resources for you guys to just make sure that you practice the material when it comes to this concept. So taking that into consideration, any questions when it comes to naming ionic compounds? Put a 2 in the chat if you want me to do a quick review on naming ionic compounds. Great. So, let's get started with reviewing really quick ionic compounds. When it comes to ionic compounds, what are the 2 required ions that I need? Let's put it in the chat. What are the 2 ions that I need for making an ionic compound? In ionic compounds, I need something positive. What is that called? Thank you, Katie. You need a metal, non-metal. But if you have something positively charged, what is the name of that ion? In ionic compounds, we need, great job, we need a cation. And like it was placed in the chat, we need something that is negatively charged, which we call that an anion, okay? Now, when it comes to this, we're going to have different types of cations and anions that you guys need to be familiar with. So let's start with the cations. The cations can come in the form of a metal, okay? And similar to what I was explaining a little bit earlier before class, if you are a metal that live in 1A, your charge is +1. If you live in 2A, your charge is +2, except beryllium. If you are 3A, your charge is +3. But that only applies to aluminum, gallium, and indium. Okay? Now, these metals that are in 1A, 2A, and 3A are known as type 1 metals. The logistics of why they lose those electrons, okay, is because they're trying to achieve a noble gas configuration. So make sure that you check that out in the videos, okay? Now, we can also have transition metals. What is the group number that defines a transition metal? Where do they live in the periodic table? Let's put it in the chat. What is the group number that defines transition metals? Thank you, Vanessa. Group B. Now, when it comes to transition metals, understand that they have variable charge. They can be +1, they can be +2, they can be +3, +4, +5, +6, +8, okay? How do you know what is the charge of your transition metal? Well, we give them in Roman numeral. A Roman numeral is used to define their charge. Okay? Now, understand that there is an exception to the rules. There are 3 atoms that are group B elements that they don't follow that rule. And that is zinc, cadmium, and silver. Zinc is always +2, cadmium is always +2, silver is always +1. So they don't have variable charge. They only have 1 charge. Put a 1 in the chat if so far things are clicking. It's making sense, at least in the area of the cation. Glad to see those ones. Now, in this course of things that have variable charge, we also have 4 elements that, even though they don't look in group B, they have variable charge. And those are tin, antimony, lead, and bismuth. You will see them with Roman numerals because that's what they do. One more thing when it comes to the cations. The only other thing that you need to know about the cations is going to be NH4 plus. What is the name of NH4 plus? There's a question in the chat. So anytime we see a Roman numeral, that means that it has variable charge. That's correct. You will see it. If you're given the name of an ionic compound and you see that next to the name, there's a Roman numeral, that's going to be an element with variable charge. And when you verify where they live in the periodic table, most likely is group B. And if it's not group B, you're going to have tin, antimony, lead, or bismuth will be them. Okay, no takers for NH4. This is ammonium. Ammonium is the only polyatomic ion that is positively charged. So when it comes to ionic compounds, these are the 3 variations that we have of cations. Any questions on the cations? Then let's move on to the anions. There are 2 flavors of anions. First are nonmetals. Okay? And when it comes to the nonmetals, let me just crop this poppy here. This is where you find the information for the nonmetals. If you live in 5A, for the purpose of this class, we're only concerned with nitrogen and phosphorus. They are the ones that are -3. When it comes to 6A, oxygen, sulfur, also selenium, they have a charge of -2. You can see that the third column gives you the name of the nonmetals. 7A, your halogens, they're all -1. It's the same idea. They want to gain electrons. So they accept electrons because in their electron configurations, they will have those electrons live like they are noble gases. They have full valence shells. That's why nonmetals gain electrons, metals lose electrons. What is the other type of anion that you guys need to be familiar with? Polyatomic anions. When it comes to the polyatomic anions, slide 18 is where you see them. That's where they are. Know their chemical formula, their charge, their name. And when we have an ionic compound, it's always that. We're going to have a flavor of cation and a flavor of anion. It could be any of the combos here. So you can do metal, non-metal. You could do metal with polyatomic anion. You can do a transition metal variable charge with a non-metal. So you always need in an ionic compound a plus and a minus. Questions on ionic compounds? Then let's move on to the next class of compounds, which is in section 3.4. We're going over covalent bonding, okay? So covalent bonding comes from the idea that we are going to have two or more nonmetals, okay, share electrons via a covalent bond. Understand that molecular compounds is the same thing as saying a covalent compound. Same thing, okay? Now, when it comes to covalent compounds, let's understand how we are going to name them. You, again, section 3.4 is not an exam 1, that is exam 2 material. When it comes to naming molecular compounds, let's understand how that name is built. As you can see overall, covalent compounds are going to have prefix, name of the first element, in other words, the first nonmetal. Then you're going to do prefix, and then you're going to do the base of the second element followed by "ide," okay? Where do you get that information of base name in the second element followed by the ending "ide"? Look at slide 18. Step 4. Let me show you where we get it. This table. That's where we get those names from, okay? So let's establish the rules for naming molecular compounds. We're going to name the first nonmetal or metalloid by its element name, okay? Then we're going to name the second nonmetal by using the table that I just illustrated. Now, we're going to add the prefix to the first and the second name, meaning step 1 will get a prefix, step 2 will get a prefix, but let's establish something special. The first nonmetal will get a prefix if it has 2 or more atoms. So as you can see in Rule 3A, if the first nonmetal has only 1 atom, no prefix is needed. The first nonmetal only gets a prefix when it has a subscript of 2 or more. How do I know what are the words that I can use as prefix? Hey, look at them here. Mono for 1, di for 2, tri for 3, tetra for 4, 5 through 10. All of those are Greek prefixes. Penta, hexa, hepta, octa, nona, and deca. Okay? What happens to the prefix for the second word in our covalent compound? It always gets a prefix. Always. Okay? Now, there is a caveat when it comes to the prefix and your, and this is particular for your oxides. If your prefix ends in O or A, but then you have oxide as that second nonmetal, then understand that you're going to delete the last vowel on the prefix and you're going to make it one word. Let me show you guys an example. Let's say that we have CO, okay? What is the name of the nonmetal symbolized by the capital C? Let's put it on the chart, on the chat. What is the name of the first nonmetal that is symbolized by the letter capital C? Thank you, Katie. That's carbon. Now, why is it that we did not put monocarbon? Because look at Rule 3A. If we have only 1 atom in the first element, no prefix. It needs to have 2 or more. Now, the second atom, okay, which is oxygen, based on the table in slide 18 here, I'm going to, because it's oxygen, I'm going to use oxide. Remember, covalent compounds do not have charge. We're just borrowing that name. So the second word is oxide. How many oxygens do we have in that chemical formula? Thank you, Vanessa. Only 1. So why do we know that we have only 1 if we don't have anything written? Because we learned that a subscript of 1 is always omitted, okay? So if we have 1 oxygen, what is the prefix that we utilize for a subscript of 1? Let's put it in the chat. Thank you, Marta. Mono. As I mentioned to you guys in Rule 3B, when your prefix ends with a vowel and is next to another vowel, understand that this is for the oxides, okay? This is particular for the oxide. It doesn't apply to other things. For the oxides, we are going to delete this O and make this one word. Monoxide. This happens when you have oxide and there's 4, like tetroxide, pentoxide. So if you have oxide as your second nonmetal, understand that you need to be aware of this. Okay? Now, understand that there are some common names for particular molecular compounds that I want you guys to know for exam 2. So you need to know that NH3 refers to ammonia. PH3 is phosphine. CH2H4, that's ethylene. N2H4, that's hydrazine. So this table you guys need for exam 2. So to solidify the whole idea of, if I'm given a name, can I do the chemical formula? Or if I'm given the chemical formula, can I define a name? Let's practice these problems, okay? So we are going to do at least the first 5 when it comes to this. Let's do it as a group. First compound that we have here. Let's go through the rules. The first element, I'm going to use my highlighter tool. So my first element, which is a non-metal, and this is my second element, okay? So the first non-metal gets the element name. So when we have a capital S, what is that element? Let's put it in the chat. Great job, sulfur. The second word, okay, is going to be based on that table that I showed you guys on slide 18. We're just gonna borrow that word. Remember, in covalent compounds, we do not have ions. They share electrons. So because oxygen is my second nonmetal, based on the table in slide 18, what would be the word that will describe the oxygen in the context of this covalent compound? Great, I already see that people are getting the hang of it. It's going to be oxide. And since we have one, similar to what the example that I just gave a moment ago, we're going to say mono oxide, but because we end in O and this one starts in O, we make it one word, monoxide. Let's do letter B, CO2. What will be the first word? Based on the capital C. Great. Carbon. Now we have 2 oxygens. How do we describe that? Great job. Dioxide. That's the second word. Let's do letter C. We have 2 of capital S. What do we use to describe that? We have 2 of capital S. How do we describe that? Thank you. Yes, di what? Not sulfide. Remember, the first non-metal, you just put the name of the element. For the first non-metal, just the name of the element. Great, disulfur. Okay, now we have 6 of the F. What is the prefix for 6? Great, hexa. And then based on the table in slide 18, what is the word that we use for describing that second nonmetal? That's fluorine, but look at the table. Thank you, Elizabeth. Fluoride, but let's spell it correctly. F-L-U-O-R-I-D-E. Fluoride. So it's fluoride, F-O-U-O. If you do O-U, that's fluoride. So no fluorides, you guys. It's not flour, it's fluo. I always take advantage of speaking Spanish when I'm spelling all of this. That's how I learned it when I was an undergrad. I'm going to give you guys a couple of minutes. Let's do D and E. So I'm going to give you guys 2 minutes to do D and E. If anybody's ready with letter D, let's put it on the chat. That is a great attempt. The first word is correctly. Is written correctly. Diphosphorus. The second word, it was deca oxide. Remember that I told you guys to be careful with the deca oxide? Hey, you tried. I'm happy. Look at what happened with the oxide. The prefix and in a letter, and then we have oxides. So what happens to the A? What happens to the A? The A goes away. So that becomes all one word. Decoxide. So remember, if your second word is oxide, write it down. If your second word is oxide and your prefix ends with O or A, they go away. Put a 1 in the chat if I just need to write it in words. Because there's some visual learners and you will verify from it. No problem. When the second nonmetal is oxide and the prefix ends in O or A, they go away. So what that means is that we can have tetroxide, pentoxide, monoxide, etc. Understand that the letter I is not affected. So if you have dioxide, you keep the I. It's only for O or A. Okay? Let's look at letter E. What would be the first word? N2. What would be the first word in letter E? Great job. Dinitrogen. Thank you for participating, Katie. That's awesome. When we have 4 oxygens, what's the word that we use? 4 oxygens. Tetra. And then what's the word that describes oxygen as the second nonmetal? Oxide. So great job, Elizabeth. It's one word. Tetroxide. Okay? Make sure that you practice when it comes to this. In Canvas, I also placed a resource for you guys to practice naming. It's a website out of, I think, Oklahoma State University, where you can just practice naming for molecular, for ionic, chemical formulas, whole names, so on and so forth. Make sure that you check it out. Now, what if I'm given the name and I need to write the chemical formula, okay? The first one, which is nitric oxide, you may be like, oh, wait, nitric oxide, I know that it has oxygen. How do I get that? Because it has no prefix here. So let's put in the chat, looking at this table, what is nitric oxide's chemical formula? Thank you, guys. Thank you, Vanessa and Rose. No, that's nitric oxide. No. See, this is how I try to make chemistry fun when I was in undergrad. Like I'll be memorizing it like that, like nitric oxide. No, that would keep me at least entertained with, oh, okay, I will never forget the chemical formula for it. Let's do the next one. Tetra Phosphorus. So what is the element? What is the symbol? If we have Tetra Phosphorus, what do we use? Not pH3. What is phosphorus? P. What is tetra? Tetra. Great job. Look at the next one. Tribromide. There you go. P4Br3. Great job, you guys. Br3. Dinitrogen. How are we going to show that dinitrogen? Let's put it in the chat. See, you guys are getting the hang of it. This is not that bad. At first, it feels overwhelming, but not that bad. Trioxide. How do we show it? Excellent job. N2O3. Letter D, disulfur. So how do we show the disulfur? Excellent. Heptoxide. How do we show heptoxide? Thank you, Marta. O7. Then we have arsenic. What's the symbol for arsenic? Symbol for arsenic. Great job, AS. And if it says trichloride, how do we symbolize that? Awesome. So as you can see, going from name to chemical formula in molecular compounds, a little bit easier because all you have to do is symbol, subscript, whatever it is, unless there's a subscript of 1, and then symbol, subscript. Great job, Atasia. Any questions on going from chemical formula to name or chemical or name to chemical formula?
I do have a question. For the exam, spelling counts for this, right?
We are not going to be doing covalent. We will be doing ionic, and yes, indeed, spelling count.
Okay.
So you you will be typing in, okay, your answers. Let me give you guys a disclaimer. So please do not engage in these activities. So I'm just going to be clear with you guys. Please do not Google the stuff that I give you. I have already Googled it, and I know that Google is going to give you the wrong answer. Apply the rules that you learn in class. Please don't be going like, oh, I'm just going to Google the chemical formula that will give me the name. Most of the time, you will get it incorrectly because I already Googled it. And I know Google has good information, you guys, but Google has bad information too. And I'm trying to get you guys used to the idea of like knowing to apply the rules. Please don't Google these things. It doesn't matter if we're going from chemical formula to name to chemical formula for ionic compounds. Just get used to the systematic way in which we do naming. It is something that as long as you can have an outline of the rules, which again, I will be discussing on Thursday, please don't follow the trap of like, oh, I'm just gonna Google it, because the 120 minutes will go by fast. Okay, so I'm going to discourage you. It's your choice if you choose to, but I want to discourage you from Googling answers because, you know, more chances than none, the answer that you get in Google is incorrect. Okay. Excellent. So one of the things is that technically the way that this chapter is mapping, the next topic that we have is the mole and counting atoms, okay? But what I'm going to do right now is to actually jump to section 3.6, because section 3.6 has to do with the concepts that you guys have for lab 3. And I want to at least have a video in which I explain all of these concepts before we get into the math of chapter 3, okay? So we're going to go through 3.6, then we're going to backtrack to 3.5, because 3.5 is just allowing us to count atoms and molecules. And section 3.6 actually talks about the shape, and this is something that is coming in the online lab for lab 3. So let's get started with getting covalent compounds into shape, okay? So far we know that when atoms come together, so the elements in the periodic table, they're going to be making ionic compounds, as you can see, and you can make covalent or molecular compounds. Now, we learned already that in ionic compounds, what is going to happen is that there's going to be a transfer of electrons, and you guys can see here how calcium, the 2 valence electrons that it has, is transferring to chlorines, 2 chlorines each, and that's how we illustrate how an ionic compound accomplished this. Now, when it comes to covalent compounds, we know that covalent compounds are going to be sharing electrons, right? And for example, here we have 2 nonmetals, fluorine and fluorine. When fluorine looks at another fluorine molecule, they form what is called a diatomic molecule. And in a diatomic molecule, we have two of the same elements. There are a series of other elements that also form diatomic molecules. And as you can see here, hydrogen is diatomic, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are the 7 atoms that form what are called diatomic molecules. All of these, because they are nonmetals, they're going to make covalent compounds. So when we go back to the example of fluorine, we can see that first we need to establish how many valence electrons our atom will have. What gives us the number of valence electrons, the group or the period? Let's put it in the chat. What information from the periodic table gives us the number of valence electrons, group or periods? Great, group. Now, which group does that trend actually follow? Group A or group B? Let's put it in the chat. Thank you, Dominic. Thank you, Isaiah. Exactly, group A. Okay, so the number before the letter A tells you how many valence electrons a particular atom has. So fluorine, because it lives in 7A, that's why it has 7 dots. Okay, that's where it comes from. Now, because that is important to know, what is the only element that doesn't follow that trend? It lives in 8A. There's only one element that doesn't follow that. It's not bromine. It lives in 8A. The group number does not correspond to the number of valence electrons. It's not aluminum. It's in 8A. Thank you, Katie and Kiyomi. Helium. Helium is the only one that doesn't follow that rule. Helium, even though it's in 8A, it only has 2 valence electrons, okay? So let's get back to this. So when fluorine meets fluorine, they're going to share electrons, okay? And those shared electrons is what we know. Let me make this a little bit thinner. As a bonding pair. A bonding pair of electrons, we can also symbolize it by a line. And that is what a covalent bond is. It's a pair of shared electrons. If you have electrons that are not shared between 2 atoms, that's what we know as a lone pair. So all of these guys, those are lone pairs. They are not shared between the 2 atoms. So in this section, we're going to learn how to build Lewis structures. These are the rules for Lewis structures, okay? Number 1, we're going to add up the total number of valence electrons for each atom in the molecule. We're going to see that if we have polyatomic ions, that's going to affect our count, because if they are negative polyatomic ions, then we're going to add electrons. If they're positive polyatomic ions, we're going to reduce the number of electrons. We're going to write the symbol of the central atom, okay? And then we are going to be forming bonds around that central atom, okay? Then the rest of the electrons in step 3, we are going to distribute them according to the octet rule. So how many electrons in the octet rule? If it's octet, what does that mean? Great, 8. Now there's some exceptions, but we will talk about them. Now, if there's not enough pairs for the central atom to have their octet, we're going to bring electrons in from the outside atoms. But in the case that there are some times when we build these structures, extra electrons, we'll just stick them in the central atoms. The best way to illustrate all of this is by practice. So, as I mentioned, there's some exceptions to the octet rule, and these are the ones that you guys need to know. Hydrogen doesn't want 8 electrons around it. A hydrogen only wants 2 electrons to share, and that's it. So whenever you have hydrogen and you bond it to a central atom or you bond it to any atom with a line, you're done. Hydrogen doesn't get dots. Beryllium only likes 4 electrons. So beryllium usually has 2 single bonds and it calls it a day. Boron only likes 6 electrons. So because it only likes 6 electrons, the minute that you put 3 bonds around it, you call it a day. But again, we are going to practice in order to understand this. Let's go through the steps one by one so we can illustrate how we actually do this. So I'm going to do the first example with you guys, H2S, okay? So when I look at this chemical formula, I have 2 atoms, hydrogen and sulfur, okay? Now that I have hydrogen and sulfur, I'm going to put what are the subscripts for them. Hydrogen has a subscript of 2, sulfur has a subscript of 1. Now, hydrogen lives in group 1A, so that means that it has 1 valence electron. Sulfur lives in 6A, so it has 6 valence electrons. So I'm going to multiply the subscript by the valence electrons. So for hydrogen is 2 times 1. For sulfur is 1 times 6. So this equals 2. This equals 6. What I'm going to do after that, add these 2. So I have 8 electrons available for bonding. Okay. Take a moment, do the same for HCN. And let's put in the chat, what is the result? How many electrons available for bonding for HCN? You can see the example of H2S. Let's do it for HCN. Thank you, Maria. Hydrogen, carbon, and nitrogen. We have 1 of each. This lives in 1A. This lives in 4A. This lives in 5A. So the hydrogen times 1, the carbon times 4, the nitrogen times 5. 1, 4, 5. When we add them, that's where we get the 10. Okay? Put a 1 in the chat if so far A and D make sense. Good. I'm going to do letter E for you guys. No problem. If 1 doesn't make, put 1.5. I'm getting there. So we have CO3, but we notice that CO3 has a -2 charge. So here we have carbon and we have oxygen. We have 1 carbon, we have 3 oxygens. Let's put in the chat, how many valence electrons is carbon giving into this system for bonding? Great. How many oxygen? Excellent. So you're going to say, okay, 1 times 4, that's 4. 3 times 6, that's 18. So at first you calculate 22 valence electrons. Now, in this atom, see how we have a -2 charge? That is also taken into account when it comes to this. So because we have a -2 charge and we're counting the valence electrons, we're going to do +2 electrons. Because we have a -2 as the charge. So for example, if you had the opposite, let's say NH4, this is a positively charged. In NH4, you have nitrogen, one of them, hydrogen, 4 of them. Every nitrogen contributes 5 valence electrons. Any hydrogen, 1 valence electron. 5 plus 4, we have 9 electrons for bonding. But notice that this is a positive charge. We're going to subtract 1 electron. So technically for this, we only have 8 electrons available for bonding. So if you have a negative polyatomic ion, do not forget to add electrons to your valence electron count. So for CO3, the total number of electrons available for bonding is 24. But if you have a positively charged, and ammonium is the only one that you guys know in terms of the polyatomics, remember to subtract. So since we did the example of CO3, take a moment and do F. How many valence electrons available for bonding on F? Let's put the number in the chat. How many valence electrons available for bonding on letter F? Close, but not quite. That's not the answer. Nope, that's not the answer. Look at the trend, you guys. Let me do it because I don't see the right answer in the chat. We have 2 atoms, chlorine and oxygen. We have 1 chlorine, we have 2 oxygens. How many valence electrons does chlorine have? Great. How many valence electrons does oxygen have? Great. So here we have 7. Here we have 12. Oh, I saw that somebody put the right answer. Awesome. So at first, we're going to count this, and you guys are going to say 19. Sorry, the feed is slow. I saw that people put the right answer. Then this is -1, so we're going to add 1 electron to the electron count. So for the people that answered 20, you're correct. That's how we get that number. Questions on counting the number of electrons for any atom? How many electrons for BeBr2? How many? Great job. Yes, 16. Okay. Just want to make sure that you guys know that. Now, let's go into building these Lewis structures. So here we have H2S. One of the things about Lewis structures is that hydrogen is never the central atom. Never, ever, 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 ever hydrogen is the central atom. So sulfur is our central atom. Hydrogen needs to be attached to it. Most molecules, when we are building them, they are symmetrical. So we put a hydrogen right here and a hydrogen right here. So these lines represent 2 electrons, okay? So towards the bond in the left, we use 2 electrons. The bond towards the right, we use 2 electrons. So that means that we use 4 electrons available for bonding. So we only have 4 electrons left. I mentioned it a few moments ago. Does hydrogen get dots on it? Yes or no? It should be immediate. Does hydrogen get? Great job. No, 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 no. I like to see those no's. So hydrogen is happy because hydrogen doesn't want an octet. Hydrogen is like, I only need 2 electrons and I'm sharing them with sulfur, so I'm good. So who gets the 4 electrons? Sulfur. 1, 2, 3, 4. So I put the 4 electrons on sulfur. I use all my electrons available for bonding. This is the Lewis structure for H2S. Okay, let's do BeBr2. Okay, we have Be and we have Br2. Okay, the central atom is going to be our beryllium. Okay, how do you know that that's going to be the central atom? Because that is the element that is the least frequent in the system, meaning that we only have 1 atom of it. So most likely that is the central atom. Carbon is another typical central atom, okay? So B is our beryllium, is our central atom. We're going to stick our bromines next to it. We're gonna make our molecule symmetric. How many electrons did I use by writing those lines to boron? To bromine, sorry, not boron, sorry, to bromine. We use 4 electrons, so minus 4 electrons. That means that I have 12 electrons available for bonding. So when I'm putting the octets, I always have to do it from the outside atoms first. So if bromine is sharing 2 electrons with beryllium, okay, it needs 6 electrons to have an octet. Because it already has 2, then 4, 6, 8. So remember, I already accounted for these. These are these guys. So the dots that you see me put here, that's minus 6 electrons. We have 6 electrons left. So how many electrons does the bromine on the left need? Also 6 electrons. 1, 2, 3, 4, 5, 6. Minus 6 electrons. We used all of our electrons available for bonding. And we're done because beryllium doesn't want an octet. It breaks the octet rule, okay? It only needs 4 electrons, so that's done. Let's deal with HCN, okay? So we have hydrogen, we have carbon, we have nitrogen. Whenever you're given the chemical formula, these atoms that are lined up like that, that means that the one in the middle is the central atom. So we have hydrogen bonded to carbon, bonded to nitrogen. I only have 10 electrons to play with. My skeletal structure already took care of 4 electrons. So I only have 6 electrons left. Can I put any dots on hydrogen? Excellent, we can. So, but we need, all of these atoms need an octet, right? The only 3 elements that don't get an octet is hydrogen, beryllium, and boron. That's it. Only those 3. Everybody else gets 8 electrons. So, how many electrons does nitrogen need in order to form an octet? Great, 6 electrons. 1, 2, 3, 4, 5, 6. Oops, I used all my electrons available for bonding. Who still needs an octet? Great, carbon. Excellent job. So how are we going to make carbon have an octet? Nitrogen is going to be so nice that it's going to share electrons with it until it receives an octet. Carbon already has 4 electrons around itself that are being shared with the atoms. So if it has 4 electrons that are being shared, in order to get to 8, how many electrons do we need to bring in and share with carbons in order for carbon to get an octet? Great, 4 more. So who is going to give those electrons? Nitrogen. That's how, you guys, we have the development of double bonds and triple bonds. Any questions when it comes to Lewis structures?
Yeah, so why wouldn't you do, like, instead on the carbon, like the dot on top and the dot on bottom, and then a double bond to the nitrogen, and then 3 dots around the nitrogen?
Because when we have the 3 dots around the nitrogen, that means that those are radical structures. And these molecules don't like to form radicals. You can have shared electrons and you can have lone pairs. Radical chemistry is specifically, we observe it in elements like the halogens. And whenever we're explaining this goes more to the fact of, hey, all of these elements want to achieve a full valence shell. For the majority of the elements, they want 8 electrons. There's only 3 that don't want an octet: hydrogen, boron, and beryllium. Everybody else wants 8 electrons. How they achieve it, it depends on the availability of valence electrons in the molecule.
Okay, thank you.
No problem. Should we do one more? Let's deal with CO3. Carbon is our central atom. Is bonded to oxygens on every single side. Okay? Put a 1 in the chat if so far that structure makes sense. Carbon is in the middle, the oxygens are attached to it. Awesome. So these bonds between carbon and oxygen took care of how many electrons already? Excellent, 6 electrons. So we're going to do here minus 6 electrons. So we still have 18 electrons to place here. All of these elements want an octet. Carbon wants 8 electrons, oxygen wants 8 electrons. Now, we always have to fill the octet from the outside atoms in. So it doesn't matter which oxygen you pick, wherever you start with, how many dots do we need to put on oxygen in order to achieve an octet? How many dots? Not 2, not 4. Oxygen is sharing 2 electrons. It needs to get to 8. Exactly. It needs 6 dots because it's sharing 2 electrons with carbon. 1, 2, 3, 4, 5, 6. Put a 2 in the chat if you understand why I put 6 dots around oxygen. What about the oxygen on the top of carbon? How many dots does it get? Great. Also get 6. 2, 4, 6. Because with the 2 electrons that it's sharing with carbon, it's octet, minus 6 electrons. We only have 6 electrons left. Who is going to get those 6 electrons left? The oxygen. 1, 2, 3, 4, 5, 6, minus 6 electrons. We have used all our electrons available for bonding, all 24. We are already in the structure. Now, there is one atom that is not happy because it wants an octet, but it doesn't have an octet. Who doesn't have an octet? Great, carbon. So how are we going to make carbon have an octet? How is carbon going to get an octet? Great job, through a double bond. Now, this double bond, it doesn't matter if it's from the oxygen on the right, the oxygen on the left, or the oxygen on top. You just have to pick one. And the way that we do this is that we go ahead and erase the 2 dots and share them as a bond. So you can see here, when we observe the number of electrons in the system, remember, we only have 24 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's where those 24 electrons are. And every single atom is stable because they are all sharing electrons. So everybody has an octet. This molecule is an ion. Sometimes ions, we put them in brackets and we put the charge outside. Okay, it's just good practice. Sometimes you will see it, sometimes you will not. But this is how you build the Lewis structure for CO3 2-. That is carbonate. On Canvas, for those of you that may want to get ahead of the game and start working on the stuff for Lab 3, I put resources from YouTube to know how to do Lewis structures, how to do naming. Make sure that you reach out by email or come to office hours if you have questions. This is all for today. On Thursday, we are going to review for exam 1. So please come prepared and with questions. Thank you guys so much for coming today. Have a good night.
Thank you.
You're welcome.